Okay, so what we're going to talk about today is a distribution of the sample mean and what that means. So we're starting a new chapter, chapter 8, and we're going to be using this normal distribution concept throughout pretty much the rest of the class. So we're going to carry right over with that normal curve into a distribution of a sample mean. Now let me just give you a little bit of an upfront notion here. When you do a distribution of the sample mean and it's a normal curve and it works off the normal curve, the mean is going to stay the same as it was for the distribution that you're sampling from. The standard deviation is going to change only slightly. So the mean will be the same, the standard deviation. I'm just trying to get this little kind of a switch in your mind to remember that the mean, when you calculate the mean, it's the same. When you calculate the standard deviation, it's going to be the old standard deviation divided by the square root of the sample size n. Okay, right now that doesn't sound familiar to you, but I just want to put that little notion in your mind so that you remember, okay, use the same mean, but recalculate or recalibrate what your standard deviation is going to be. So okay, somebody asking a question? Okay, if you're not asking a question, please mute your mic. All right, we're going to move on to distribution of the sample mean. And we've got two types to think about. One is if the population that we're working with is normal. Hey, Yolanda?
Yes.
Could you mute your mic unless you have a question?
Okay, sorry.
That's all right. All right. So distribution of the sample mean, we've got two situations. We could be working with a normal population like temperatures, body temperature. So we decided that's a normal curve. So the underlying random variable could be normal. The other thing is we could be working with something where the underlying population is not normal. And so we'll distinguish between those two as we go. Okay, so X bar is just a sample mean. So if we took 10 people and measured their height and then averaged their height, that would be the mean for that sample. So X bar is just a sample mean. Now, if we take, what do we mean by the sampling distribution of sample means? Okay, so think of it like this. If we were to take, first thing we have to do is come up with a number for our sample size. So sample size n, we could say like n equals, say, 30. Technical difficulties here. Okay, so once you figured out what your sample size n is going to be, then you've kind of established a basic notion that you need to create a distribution of sample means. Because what you're going to do is you're going to pull all of the sample size 30s that you can from your population, and you're going to get X bar for each of those groups of 30. So we call the sampling distribution, it's a probability distribution for all the possible values of the statistic computed from a sample size of n. So if I went out and got, let's say that our population is all of the students at Cali College, and that I lock in a sample size of 30, and so I grab 30 students into a random sample at a time, and I calculate the X bar for, let's go with body temperature. And let's say that the X bar for that whole group of students is like 98.1. And then I go, so we'll just call this group 1. And then I go get another group of 30 students, and I calculate the mean temperature from that group, and it comes out to be, say, something like 98.3. And I go get another group of 30, and I calculate their X bar, and that turns out to be, say, 97.9, and so on. There's only so many unique groups that I could get from the population of all students at Cali College, where there's 30. Now, if I got a group where I only changed one individual, then that's still a new group. So if I were to pull every possible unique group of 30 students from Cali College and then calculate the mean temperature, body temperature for that group, I've got all these different numbers. Well, we're going to throw all these numbers into a bucket, and that's a bunch of numbers, and those numbers represent a distribution of exactly what they are, sample means. And in this case, it's of size n equals 30. I could create a whole nother distribution with n equal only 15. So then I would only pull 15 students in and create some X bar out of 15 at a time. And, you know, maybe we get 98.3 for the first group, second group, and so on. And the only difference between this distribution, we throw them into a bucket, is that for this distribution, n was 15, and for this distribution, n equals 30. Okay, so if you think about it, if capital N is the population size, then I'm choosing little n at a time, and that's the possible unique samples of size n from a population of size capital N. Okay, so that's kind of the main idea of what we're saying when we do a sample distribution of the sample mean. Let's drill down on some more basics here. So if we're going to go about this, we have to obtain a simple random sample of size n, whatever we've locked in as our sample size for this distribution we're going to create. And then compute the sample mean. And if it's a finite population, like all students at Cali College, then we can repeat these two steps until every distinct simple random sample of size n has been obtained. So every student has been represented in a sample, and many times, as long as somebody, in each of the samples that you are included, there's somebody that's different than from another sample that you were included in. So we're talking about a big number here. Okay, So now that we've created a probability distribution of all these sample means, we can ask things like, what's the probability of getting a sample mean that's between 99 and 101 if our sample size is n? So going back to the temperature notion, I could say, hey, if I lock the sample size of students to 15, what's the probability of getting a sample mean that's between 97 and 98? Okay, so we get to start treating it like its own little sample distribution. Okay, so let's look at an example here. We've got, we happen to have a normal population to begin with, so that's what this is saying here. And the normal population is the weights of pennies minted after 1982. They're understood to be approximately normally distributed, and the mean of that distribution is 2.46 grams, and the standard deviation is 0.02 grams. Okay, so right now we're not talking about a distribution of sample means, we're talking about a distribution of penny weights, and it happens to be a normal distribution with a mean 2.46 and a standard deviation of 0.02. So we could draw our little normal curve for these pennies and have our mean 2.46, and then just count 0.02 over to get one standard deviation away. So this would be 2.44, and this would be 2.48. Okay, so that's we're talking about weights of pennies. Okay, now let's talk about a sampling distribution of sample means. And we do that by obtaining, we're just going to grab 200 simple random samples of n equals 5 from this population. So what we end up with is all these different sample means where we grab 5 pennies. So instead of weighing 1 penny at a time like we did in the normal distribution that we started with, we're going to grab 5 pennies at a time and average their weights and treat that as a single unit in our new distribution. So now if we look at some of the results of this, so somebody went to a lot of trouble here. The first 5, the first sample of n equals 5 had these values. So x bar, if these are the 5 penny weights, is to, if I calculate the average of these 5, I get 2.444. And then I'm going to do that a bunch more times, and we end up with 200 different readings of sample size 5 average weights. So none of these are individual penny weights. They're all penny weights of averages of 5 at a time. Okay, so this represents a sample distribution of sample means with n locked in at 5. Okay. Any questions or thoughts? If something's not clear for you, just speak up. All right, so if we then take the mean of those 200 sample means, look what happens. We had so much data there that we ended up getting the exact same mean as the underlying population if we took the mean of our sample means. So that's pretty powerful. Even though we've only got 200, we don't have every penny in the world. We've got 200 sample means at 5 at a time, but the mean of those means turns out to be identical to the mean as the underlying normal population. Now the standard deviation, let me ask you this. Would you expect the standard deviation to get larger or smaller if we change to a sample distribution of sample means?
Smaller.
Okay, smaller, and why?
It narrows down the data set.
Okay, so each time you're looking at an individual unit, you're looking at an average of some group. So they should together have a better representation of the mean, or be together, their average should be closer to the true mean. So every time we increase n, we should expect to see our standard deviation shrink, and that's exactly what happens. If we were to take a look at the standard deviation of the sample means, it turns out to be 0.0086, whereas in the underlying population, it was 0.02. So it's a much smaller number now, but the mean itself did not change. So that's what I was saying up front, is when we get a new distribution of sample means, we're going to carry over the mean from the underlying population, but we're going to shrink the standard deviation by the nature of having more data into each single value, included in each single value. Okay, so now let's take a look at a histogram of the sample means. And remember, this is with n equal 5. It's kind of got the bell shape. You could argue that it's not, a perfect bell. It looks like this highest point is a little more favored over here than it is here, but it's pretty bell shaped. I think if I had to pick one, I'd pick bell shape. And remember that the underlying distribution of pennyweights was normal, so that makes sense that if the normal curve was there to begin with, it should stay throughout. Now, if we approximate the sampling distribution of the sample mean with 200 random samples and we change our size from 5 to 20, here's what happens. And remember that our original mean was 2.46 and that our original standard deviation was 0.02. But just by changing the size from 5 to a larger size of 20, now we're using more pennies to create each individual X bar in our distribution. So here's what happens. When the mean with n equal 5, we get this. With n equal 20, we get this. But notice that the dispersion is again shrunk. So with n equal 20, the mean is still 2.46, but the standard deviation is now 0.0045, and that's even smaller than when n was 5, when the standard deviation was 0.0086. So bump n up, and we keep shrinking sigma. Okay, so basically it's just there's less variability in the distribution with n equal 20 than n equal 5. So how do we calculate that new standard deviation? Well, one thing we're going to do, first of all, is we're going to distinguish a mean for a distribution of sample means. We're going to distinguish it from mu itself by calling it mu of x bar, because it's the mean of a bunch of x bars, or a bunch of means. But it turns out that it's identical to the underlying mean. So mu x bar is the same. That's what we said. Here's the difference when you calculate sigma for x bar. It's not just flat out sigma. If I want to calculate sigma x bar, I got to take the old original sigma and then shrink it by dividing by the square root of our sample size. Okay, so these are how you get those all-important mean and standard deviations for a distribution of sample means. Okay. Let's talk a little bit about the shape. If I create a distribution of sample means, then if the underlying distribution, such as body temperature or penny weights, is normal, then so too will be the distribution of x bar. So the shape of x bar, if x is normal, is also normally distributed. Okay, x is normally distributed, x bar sample means are normally distributed. Hopefully that's not too surprising. Okay, so let's talk about this in terms of calculating the mean and the standard deviation. It's pretty easy if you consider. The weights of pennies minted after 1982 approximately normally distributed with our mean 2.46 and standard deviation of 0.02. what's the probability that in a simple random sample of 10 pennies, so let's just identify that n equals 10, we're sampling 10 at a time, minute after 1982, we obtain a sample mean of at least 2.465 grams. So let's write in terms of a probability, generic probability statement, what that's saying. That's saying what's the probability that X bar is at least, so that means greater than or equal to 2.465. Okay, well, we know that since the underlying pennies were a normal distribution, so too is sample means of size 10. So all we need to do is figure out with n equal 10 that mu of X bar, well, that doesn't change, so we're going to use 2.46. But we have to recalibrate sigma for this. It's going to be the old sigma of 0.02 divided by the square root of whatever our sample means sample size is, and that's 10. Okay, so turns out to be about 0.0063. Okay, so we've got those parts. Well, I can tap right into, we can look up a 2.465 and convert it to a z-score. Or if I wanted to directly calculate this off my calculator, I now have enough information to do a normal CDF. And since we're doing a greater than or equal to, my minimum is going to be 2.465. And then my maximum is going to be calculator infinity. And then remember, I need to use the original mu for mu X bar. But sigma X bar, I recalculated to be 0.0063. Okay, so that's going to answer this question. Let's look at the normal image here for it. I'm going to shrink this one or two. All right. Okay, so this is the same problem. It's just showing us the normal curve, a few more steps. X bar is normally distributed, and then we calculated the new, with a n equal 10, the new sigma for X bar. And then if we convert our X score to a Z score, we're going to take the X value in question. Remember, it was a probability of getting X bar greater than or equal to 2.465. So this would be equivalent to a probability of Z being greater than the 0.79. So if we go look up a Z-score for 0.79, that gives us the less than, that gives us this area that's white. Since we're calculating the complement of that, we'll go ahead and complement it, and we get an answer of 0.2148. Okay, if you had your calculator and you try the normal CDF that we did up here, you can verify that you get the same thing. Or at least close to it. So if anybody has done that, great. Okay, any questions here before we move on? What's going on with the sample distribution of sample means? Okay. All right. So that's great if your underlying population was normal to begin with. Okay, so let's put that aside, and now let's talk about another situation where the underlying population itself is maybe not normal. Maybe it's a uniform distribution, maybe it's way skewed right or skewed in either direction. So what happens to the distribution of sample means if our sample comes from that underlying population that's not normal? Okay, so that's what we're going to start talking about here. Think about if you roll a fair dice, there's 6 sides and they all have equal chance of coming up. That makes it a uniform type of distribution for all 6 outcomes. So mu, if you calculate mu, and we would get 3.5, which is not even a possible outcome on rolling a dice, but that's the average. And the standard deviation for this distribution is 1.708. Okay, so, but we don't have a normal underlying population. But since we're given these values, now let's start talking about if we were taking samples of 5 rolls at a time, or 10 rolls at a time, or 30 rolls at a time. Okay, so what I want to do is just walk you through some of the outcomes. If we take and we lock sample means for rolls 10 at a time, let's start with 4 at a time. Okay, so this is the shape we get out of a distribution of sample means when we roll and average 4 rolls at a time. Most of the time we're getting something near the mean, and the rest of the time we get fluctuations on either side of it. It's not a great bell-looking shape. It's a little heavier out on this side. We're going to bump our sample size up to 10, and this is what we get for the shape of the distribution of sample means. Now look what happens once we hit 30. 30 is kind of that special law of large numbers for sample sizes, and it's also where the distribution takes on a pretty recognizable bell shape. So we're going to lock this in and say with n equal to 30, the sample means take on the more distinct bell-shaped curve and appear to fit the normal model, even though just a roll of a dice itself as a distribution does not have a bell-shaped curve. It's got a uniform shape. So plug that distribution into sample means, and as long as your sample size hits about 30, you start to get an acceptable normal distribution. Okay, so what we're going to say then about this is that the shape of the distribution of sample means becomes approximately normal as the sample size n increases, regardless of the shape of the underlying population. And what's nice about it is that we calculate mu just as we did before, and we calculate sigma just as we did before. Okay, so what we need is, based on the central limit theorem, we need a fairly large n. So to accept the sample distribution of sample means, the normal assumption or sample size should be n equal 30 or greater. If the underlying population is not a normal distribution. Okay, so we've got enough background here now to actually make this effective in terms of just a generic few problems here. So let's look at the mean time for an oil change. So this particular location, the mean time for an oil, the 10-minute oil change place is 11.4 minutes, and their standard deviation is 3.2 minutes. So if we get a random sample of n equals 35 oil changes, let's describe the sample distribution of the sample mean. Well, we've hit that upper limit of 30, so 35 meets the requirement. So they didn't even tell us whether oil changes itself is a normal distribution. All they told us was that the mean is 11.4 minutes and the standard deviation is 3.2. But since n was greater than 30, we're okay. So we're going to keep the same mu of 11.4, but we're going to calculate sigma for our x bar of 3.2, the old standard deviation, divided by the n equal 35 sampling size, square root. Okay, so that's 0.5409. Okay, now what do they want to know? If a random sample of n equals 35 oil changes is selected, what is the probability that the mean oil change time is less than 11 minutes? So they're saying, what's the probability? No, no, thank you. Basically what they're saying is find the probability of x bar coming in at less than 11. And since n equals 35, we have to use the new standard deviation that we calculated before. So the new standard deviation is 0.5409. So when they create the z-score, they take the 11. So this is just like taking the x bar, 11 minus, this is our mu of x bar, and this is our sigma x bar. And that gives us a z-score that we can go look up in table 5. Okay, so if I wanted to use the calculator, I'm going to go ahead and pull it up and ask you guys for the inputs. And remember, I want you to be fluent both using a calculator and using table 5 by converting to standard normal. It's not what I want. Okay, so if I'm going to use this, I'm going to take normal CDF, and what's our lower bound? Well, since it's anything less than 11, our lower bound is negative, and negative calculator infinity. So I'm going to say -1 second times 10 to the 99. And our upper bound is 11. And then mu is the original mu of 11.4. But sigma is sigma of x bar, 0.5409. Okay, and we get to the nearest hundredth the same result that table 5 would give us in this example here by converting to standard normal. Okay, a couple more problems. We got Old Faithful, most famous geyser in the world. In Yellowstone Park is a mean time between interruptions of 85 minutes. And the interval of the time between eruptions is normally distributed. So in this case, we've got an underlying normal distributed. And the standard deviation is 21.25 minutes. So let's just document the underlying mean, 85, and the underlying sigma is 21.25. And since they said it's normally distributed, we don't have to worry about n size, the sample size. So n could be any sample size here. What's the probability randomly selected time interval between eruptions is longer than 95 minutes? So here, this is just a flat out p of x being greater than 95. And since they told us this was normally distributed, I can either convert it to a z-score or I can use normal CDF. So 85, or I'm sorry, minimum. So minimum's going to be 95. Max is going to be calculator infinity. And then the last two are mu and sigma, so 85, comma 21.25. And that'll give us the answer for A. Now, all of a sudden, we've got a totally different question with part B. What's the probability a random sample of 20 time intervals? So now we've got an n equals 20, and we've got a distribution of sample means. So what's the probability that a random sample of 20 time intervals between eruptions has a mean longer than 95 minutes? So B, the question is now, what's the probability of an X bar being greater than 95 minutes? Well, all we have to do is recalibrate sigma X bar off of old sigma over square root of n. So in this case, that's 21.25 divided by the square root of 20 n. And that's going to be 4.75. If I round it to the same number of decimal places as the one they gave us. Okay, so now for part B, what they're asking is normal.
I got a question real quick.
Yes.
Is that lambda or square root for the sigma over n?
Sigma over a square root of n.
Okay.
So we're going to say normal CDF, and again, we're asking for greater than 95, only this time we're asking in terms of samples means size 20, for sample size of 20. So the 85 doesn't change, but this does change to 4.75. Notice how much it shrunk the standard deviation from the underlying normal distribution when I take 20 at a time and calculate means. Okay, so let me ask you this. Which of these two do you expect to have a higher probability? Do you think that A, probability that a randomly selected time interval is going to be longer than 95 has a higher probability than a mean of 20 time intervals being greater than 95? Okay, so
I'd say a randomly selected one.
okay, and what's your reason there?
because the standard deviation is higher.
Okay. All right, so I'm going to let you guys plug that in and answer that for yourselves there. Want to move on to the next problem. I don't think we got time to go through every one of these. Here, C is just saying, hey, what happens if we change our sample to 30? So this is going to be n equals 30. So my new sigma x bar is going to be 21.25 divided by square root of 30 for C. Okay, so really this is the time if something's not clear, if you want to see anything else. Let's look at this last problem, the oil change. I hope you're not asking questions because you don't have any. Otherwise, I would really like to hear some questions. Okay, the shape of the distribution of time required to get an oil change is not known. Okay, so this is different from the last problem. We need a sample size 30 or greater if we want to be able to use normal distribution. But records do have an indication for a mean of 11.4 and a standard deviation of 3.2 minutes. So if we want to compute probabilities regarding the sample mean using the normal model, what size sample would be required where, well, we need n equal 30 or more. Okay, so let's take a look at B. What's the probability a random sample of n equal 40 oil changes results in a mean of less than 10 minutes? So B is asking what's the probability of a mean x bar less than 10? And since n is equal to 40, we're good to go. So sigma of x bar is going to become old standard deviation 3.2 divided by the square root of n. That doesn't change. So if I take 3.2 divided by the square root of 40, you get 0.50, we'll say 0.506. Okay, so if I'm going to make the z-score, don't have time to do z-score, so we'll just do normal CDF. And our min is -1 e to the 99. And to keep it less than or equal to 10, less than 10 is the same as less than or equal because it's continuous distribution. And then this is 11.4 for mu. And with 40 at a time, our new sigma is 0.506. Okay, that's good. Change this to 10. Still use 9.4. This becomes 0.506. Okay, so it's 0.0028. Okay. Okay, and so that kind of helps you decide for part C here if they wanted to pay bonuses if they meet certain goals. So they the manager will be able to tell what the probability of having to pay these bonuses is just based on the sample distribution and sample means. So, okay, I think we're gonna have to leave it there. I've got an online assignment for you set up for this section. And like I said, we'll talk a little bit more about this and sample proportions as well. And then I'll go ahead and get you the next part of that body temperature lab. Okay, so any last questions before we sign off?
So is the first portion of the body lab due tonight?
By the end of the day, yeah.
Okay. And then you'll get the second part to us, and when is that going to be due?
I'll let you know when I assign it.
All right.
All right, so anything else? Okay, so remember when you do these to be able to do it, if the problem doesn't ask you explicitly to use table 5 and use the calculator, you still want to every now and then exercise your table 5 versus calculator and just see that you're getting the same result essentially either way. Okay. All right, so like I said, your assignment will be on Pearson MyLab, and we'll meet again Wednesday, and I'll see y'all then.